Imagine a strictly controlled experiment. We place 3 identical sealed glass containers on laboratory burners and ignite the burners at the exact same moment, supplying each with the same amount of thermal energy. The only difference is what's inside. First, argon, a monatomic gas. Second, oxygen, which is diatomic. Third, carbon dioxide, a polyatomic gas. Within seconds, we see a massive anomaly. Despite receiving the exact same amount of energy, the temperature gauges are rising at 3 completely different speeds. The argon is already scorching hot. The oxygen is warming steadily, but the carbon dioxide gauge is barely moving. If heat is simply energy, why does an identical application of that energy fail to produce an equal rise in temperature across all 3 gases? These mismatched readings indicate that different gases process thermal energy through distinct mechanical pathways. Solving this mystery requires the kinetic theory of gases. During the 19th century, physicists like James Clerk Maxwell began explaining large-scale behavior by analyzing the microscopic motion of individual atoms. The solution begins by redefining what we are actually measuring. While we often use the word loosely, temperature does not measure the total heat energy in a system. This equation defines temperature as a macroscopic measurement of a molecule's average translational kinetic energy. It measures one thing: the speed at which a particle flies in a straight line from point A to point B. This creates a new question. If the temperature only tracks straight-line speed, what happens to the energy from the burners that isn't making the oxygen and CO2 fly faster? To find the missing thermal energy, we have to look inside the molecules to see how they move internally. To understand this, we need to go down to the microscopic level, zooming deep inside the atomic structure of the argon container. At this scale, energy sharing is governed by the law of equal partition of energy. This law dictates that thermal energy has no preference. It must divide itself with perfect equality among every available way a molecule can move. Each of these movement options is a degree of freedom, and the math says each one receives exactly 1/2 kBt of the total energy budget. Argon is a monatomic gas, existing as a single-point mass. Its only options are moving linearly along the x, y, or z axes. Because it only has these 3 translational degrees of freedom, it spends its entire heat budget on linear speed. Energetic, every joule of heat goes directly into making the atoms fly faster, which is why argon's macroscopic temperature spikes so quickly. Now, consider the oxygen container. A diatomic O2 molecule is shaped like a dumbbell rather than a single point. Like argon, it still uses those 3 basic translational degrees of freedom to fly through space. However, that dumbbell shape allows the molecule to tumble and spin, adding 2 independent axes of rotation. Rotating along the bond's axis has a negligible moment of inertia, so it doesn't count. This leaves oxygen with 5 total degrees of freedom. This creates a siphon effect. Let's track a joule of heat entering the oxygen molecule. The equipartition law splits this energy 5 ways. 2/5 is siphoned off into spinning the molecule, leaving less energy to increase linear speed. Because temperature only measures linear flight and rotation taxes the heat, you must pump significantly more total energy into oxygen to match argon's temperature rise. If we return to the macroscopic world, we find a measurement called specific heat capacity. This value tracks exactly how much heat is required to raise a gas's temperature by 1 degree. Specific heat is a direct mathematical consequence of this microscopic energy sharing. We can actually predict these values by counting the degrees of freedom using the equipartition math. These theoretical predictions based on molecular geometry align perfectly with real-world measurements for monoatomic and diatomic gases at room temperature. The data tables found in physics textbooks are direct translations of a molecule's hidden microscopic geometry. This brings us to the final container, the carbon dioxide, and a complication that arises at higher temperatures. Very complex molecules, or even simple gases under high heat, stop acting as rigid shapes. Their atoms begin to oscillate back and forth like weights on a spring. These vibrational modes unlock even more degrees of freedom. They soak up large amounts of heat energy through internal vibration before the linear speed and the temperature can increase. We can trace the anomaly we saw on the lab bench directly to these microscopic mechanics of energy distribution. Specific heat measurements provide a macroscopic fingerprint of molecular freedom, dictated by exactly where that energy is allowed to go.